Let's talk next about the beta function. It is one of the most useful functions in higher mathematics, and it's given by a rather symmetrical looking expression. It's the integral from 0 to 1, x to the n minus 1 times 1 minus x to the m minus 1 dx. So it's got a symmetry between x and 1 minus x. If you make a change of variable of 1 minus x equal to z, for example, where z is just a variable and not complex number, then you're going to get these two interchanged. So beta nm is the same as beta mn. It's got this nice little symmetry. So let's see how this can be used to evaluate actual integrals. Now beta function is really useful because you can actually evaluate some very complicated looking integrals. For example, if I have to integrate 0 to pi by 2 sine of 7 theta d theta. Now if you were to do this by normal means, you'll have to first of all break up sine into sine and cosines, and then maybe integrate using parts. It's pretty complicated, and you can check for yourself. The effort required is going to be tremendous. Now what we're going to do is we're going to put this in the beta function in a particular form. So one thing we can do is set x equals sine squared theta. In that thing. So what I'm going to get is dx would be 2 sine theta cosine theta d theta. Also, when x equals 0, theta is 0. When x equals 1, theta is going to be pi over 2. So the limits are going to shift. So let's write what beta of nm is with this new substitution. It's going to be integral 0 to pi over 2 sine squared theta to the power n minus 1, 1 minus sine squared theta to the power m minus 1 times 2 sine theta cosine theta d theta. Well, that's already looking pretty good. The 2 comes outside. Now I have an extra power of sine theta which goes and makes this. There's already 2 multiplies n minus 1 to give me 2n minus 2, but then there is a sine theta, so that becomes 2n minus 1. Meanwhile, 1 minus sine squared theta is cosine squared theta, so cosine squared theta makes this 2m minus 2 again, and that once again becomes 2m minus 1. So very symmetric looking expression between cosine and sine. So that's in keeping with the symmetry of that. So this is the answer we get. It's really useful, and we can use this. For example, in our case, in this particular case, we need, so what we need here is, there is nothing with cosine here. So we need 2m minus 1 to be equal to 0. That immediately solves for m. M is 1/2. Also, we need 2n minus 1 to be equal to 7. And that solves n. That gives me 2n equals 8 or n equals 4. So this integral that we have, let me call that something. Let me call this I. So the initial integral, which is I, is essentially equal to the beta function. Incidentally, the reason it's called a beta function is the Greek beta, capital beta, is b. Similarly, the Greek capital gamma is like that. So Greek beta is b, gamma is that. The lowercase is this and that. So that's the reason why these are called. Beta function is written simply as a b rather than as anything fancy like that, because this is uppercase and that's lowercase. Anyway, getting back to the non-cosmetic aspects of this problem. So that integral I have is essentially equal to bnm, so that's going to be 4, half. Now, there is an important property of the gamma function, which I'm not going to prove, but it is quite easily provable if you are so inclined to do it, and you can look at any books for this. And that is, beta of nm can be written entirely in terms of gamma functions, and this is what makes beta functions really easy to calculate, because gamma functions are about just a bunch of factorials for the most part. So I can write beta in terms of gamma like that, and here you can immediately see that there's a symmetry between beta and gamma, between beta nm and beta mn. So from this expression you can readily see the symmetry here, whereas here you need a change of variables to see that symmetry. Here too you need a change of variables. That's a limit 0 to pi by 2 here. So we can use this formula to get any further with this problem. So this tells me that the integral is gamma of 4, gamma of half, divided by gamma of 4 plus half, which is 9 halves, or 4.5. Okay. Now in the previous problem, we already know that gamma of half is root pi, but we don't really need to know that. And also in the previous problem, I calculated gamma of 9 halves. So I guess I knew what was going to come in this problem. So I'm going to write this as 3 factorial. And even if I didn't know what gamma of half is, you're going to eventually cancel it with a similar gamma of half in the denominator. So let's for the moment pretend that we didn't know what gamma of half is. And this here downstairs, I'm going to get, oh, by the way, I think I made a slight error. All that is going to be 2 times, so I need a 1/2 here because of the factor of 2 here. I need a 1/2, okay, to pull this off. So it's 1/2, 1/2. And then gamma of 9 halves, which in the previous problem I calculated, so I'll just not bother with that. 5 halves, 3 halves, 1/2 times gamma of half. So even if you did not know what gamma of half is, I mean from the previous video you know it's root pi, but even if you did not know it, it's no big deal because it cancels out. So let's see if we can simplify this. This gives me 3 factorial. I'll leave that as it is. All these 2's, there are 4 of these 2's. I'll take 4 of the 2's upstairs. Okay, so I get 2 to the power 4, and then what I have downstairs is 2. So let's try to do this. I'll write, I'll keep 7 as it is. 5 times 3 is 15. 15 times 7 is 35, so I'll write 35. And then there's another factor of 2, I guess. So that was not super efficient. 15 times 7, 35. So there's another factor of 2. So that's going to give me 2 cubed, which is 8. I think I'm doing something crazy here. Just want to make sure I did this all right. 2 to the power 4, 35. Oh, that's 7 5s are 35. They still have a 3 left. So I guess I can cancel out the 2 with also the 2 there and the 3 there. So I don't have to do this. So that gives me 16 over 35. So that's the answer. That's pretty amazing. That integral, which is not easy to do at all, I get in just a few minutes. So it's a very useful way of calculating complicated integrals. Now sometimes you may have a situation where you don't really want to calculate anything. So, but if you write it in terms of gamma functions, you can then look at tables. So that's another useful way of playing this game. So let's suppose that we want to calculate a very complicated looking integral. Normally these kind of integrals will not be able to be calculated by any calculus trick you learned in elementary grades. So let's try doing something like x dx over 1 minus x to the 5. Now u substitution will not work, because if I did 1 minus x to the 5 equals u, then du is going to be x to the 4, but I only have x. So if you do a u substitution, you're going to get even crazier things than what I have here. But I will try a u substitution, but try to make it into a gamma function. Let's try that. X to the 5 is u. That tells me that 5x to the 4 dx is du. Let's see what happens. When x equals 0, u is 0. When x equals 1, u is 1. So the limits don't get changed. So let's write this in terms of the u function. So I get integral 0 to 1. X is now u to the 1/5 times du. So by the way, du is dx times I meant to write dx equals du divided by 5x to the 4. And since x is u to the 1/5, that's going to be du divided by 5u to the 4/5. So you can already see this looking pretty ugly, and the hope is that we're going to get something slightly easier than what we started with. It doesn't look like that at all. So that's 1 minus u to the power 1/2. What do I do with this monster? Well, fortunately for us, this is not a totally ugly monster, because this is u to the minus 3/5, because 1/5 minus 4/5 is 3/5, and then 1 minus u to the negative 1/2. It's our friendly neighborhood beta function, because if you look at the basic definition of the beta function, it's got x to some power and 1 minus x to some other power. So this is just 1/5 beta of, remember the original beta function is n minus 1. So if n minus 1, so the trickiest part of beta functions is to figure out what this n is. So n minus 1 is negative 3/5, which means that n must be 1 plus negative 3/5 or 2/5. Similarly, we have to set m minus 1 equal to negative half. So this part I think you should be very careful about, because there are so many negatives here. And so m equals 1 minus half, which is half. Once you figure out the m's and the n's, then you're good to go. So that's beta of 2/5 comma 1/2. And from this point onwards, you can use this famous identity. So that's 1/5. This is sometimes called the functional identity. Because it expresses one function, which is beta function, in terms of another function, which is gamma function. It's just a name that mathematicians like to use. So I have the functional identity can be used. So I get gamma of 2/5 times gamma of 1/2, which is your favorite root pi. And then I have gamma of 2/5 plus 1/2 in the denominator. Now I'm not saying that this problem is done by any means, so I'll write root pi here over 5. I still have to deal with gamma of 2/5, and I don't know what that is, and I don't know what gamma of 9/10 is, because 9/10 is what you get when you add 2/5 and 1/2. The common denominator is 10, and that's going to give me 5 plus 4, 9. But these can be referred to, there are these functions of gamma function tables. So you can go to gamma function tables and look up gamma of 0.4 and gamma of 0.9, and it'll all be there, because gamma is defined for any complex number z, and gamma has been listed for almost everything, and there are huge tables in every book of mathematical physics that details in great variety the various gamma function values. In fact, you'll find this in the pretty early stages of any such table, because those tables go on for sometimes complex values of the argument and real values of the argument. So this will be found early on in the tables. So you can really do problems like this very expediently.